In this lesson, we're going to be continuing our look at trigonometry that we can use when we have a non-right angled triangle. So you can see I've got a triangle here, and I've tried to make it fairly obvious that we have no right angles involved. And so that means we can't use the primary trig ratios. So we can't just use sine equals opposite over hypotenuse, cosine is adjacent over hypotenuse, or tangent is opposite over adjacent. In another lesson, I talk about the sine law, and that's one way that we can deal with triangles that are not right triangles. And another way is the cosine law. So as I did before, I'm going to start with the formula for the cosine law, the relationship for the cosine law. Then I'll do a couple of examples showing how to use it, and then I'm going to show a derivation of how you actually come up with it using right angle trigonometry that you should already be familiar with. So the cosine law is a more complicated relationship between the sides and the angles, and the cosine law tends to focus on a single angle at a time. You can see that here. So in this case, I'm focusing on the angle that corresponds to the vertex A, and the rest of the cosine law has to do with that. Now, the one thing that you might notice is there's a part of the cosine law that looks suspiciously like the Pythagorean theorem. And when I do the derivation for it, you're going to see that I actually use the Pythagorean theorem. So since this is not a right triangle, though, there is no reason why this triangle should obey the Pythagorean theorem. And also, we haven't even chosen the longest side here. We've just chosen the side A and the angle A. So in addition to this very Pythagorean looking relationship, we also end up with this additional part. And so you can see the relationship between the angle A and the side across from the angle A is in terms of the side lengths of the other sides. So if I'm interested in this side A, then I also need to know the side B, the side C, and the angle across. So I use this form if I'm trying to find a side. And I would use this form, which is this same equation just rearranged. I would use this form if I'm trying to find an angle. And I think I just want you to see that these two things, where this comes from. I'm just going to open up a new page, and I want to paste this, because a lot of students will sometimes, they'll start with this, and this is by far the easier form to remember rather than the other form I just showed you. So I just want to show you that it's actually fairly simple to go between the two forms. So what I'm going to do is, I don't like this negative here, so I'm actually going to take this whole term and I'm going to move it to the left side, and then I'm going to take this a squared and I'm going to move it to the right side. So this negative 2bc cosine of a becomes positive 2bc cosine of a. And b squared b squared plus c squared stays the same. And now this positive a squared comes over here, becomes negative a squared. Now I want to isolate cosine of a, so I divide everything by 2bc, and I end up cosine of a is equal to b squared plus c squared minus a squared, all divided by 2bc. And as you can see, it actually wasn't that much trouble to go from this first format to the second format. So I really encourage people to commit this one to memory. Now there's another problem with the cosine law, not a problem, but another complexity with the cosine law, which is that this is the cosine law equation for the side A and the angle A. But what if I'm dealing with the side B and the angle B, the side C and the angle C? The cosine law actually has other forms depending on which of those you're dealing with. And if you take a look at it, this what I described as this Pythagorean-like relationship, that's pretty straightforward. If I was using a, so I had a squared equals b squared plus c squared minus, and now if I want to focus on b, I have b squared equals a squared plus c squared, or if I'm focusing on c, c squared equals a squared plus b squared. So these two that I'm adding together are always just the other two sides. And the same thing is true here. This form is always minus 2, and then the side here and the side here, in this case a and c, those are the same sides from here. And the cosine of this angle always corresponds to this side. So you can see angle cosine of the angle B, side B. Cosine of the angle C, side C. So again, if you can just remember one form of this, and in general for me, this is the part that I started committing to memory, and to be honest with you, this is the form that if I need to, I always fall back to, and I can come up with any of these other forms, whether it's the side form or the angle form, from here. So start with one, learn it very well, and then you just learn to modify it as you need. Okay, so I'm going to skip over the derivation of that for now, and let's get right into doing a question. So in this case, I'm finding the side C. I've conveniently labeled my triangle ABC, so that's nice. So the form that I want to use, already we have to make a change. So let me just show you. I remember this form, a squared equals b squared plus c squared minus 2bc cosine of a. But I want to work from the side C. So instead, c squared equals, now instead of, let's see, if I have a squared, I use the other two sides b and c. Well, if I have c squared, I use the other two sides a squared plus b squared minus 2. bc up here is matching these two sides, so this is going to be 2ab cosine of the angle C. So I'm not going to use this one, I'm going to use this one. And I go ahead and start filling things in. A squared. Do I know the length of A? I do. That's right here. This is small letter a, and that's 5.9 all squared, plus b squared. This is the side b equal to 5, so that's going to be 5 squared, minus 2 times a, which is 5.9, times b, which is 5, times the cosine of the angle C, which is the cosine of 50 degrees. C squared is equal to, now this is something you could do all in one step on your calculator, or you could divide it up into multiple steps. I'm going to go ahead and just put it in my calculator as is. I'm using a different calculator than I'm used to here, so there's my squared button, plus 5 squared, which of course is just 25, minus 2 times 5.9 times 5 times the cosine of 50. I make sure my calculator is in degree mode, and I end up with approximately 21.8855. 8855. And so C is equal to plus or minus the square root of 21.8855. But of course C is a side length, so I'm going to say that C must be greater than 0. So C is approximately equal to, and I take the square root of this, and I end up with 4.7 as my answer. And to double check that, actually I don't need to double check that in this case, because I can see that I've actually given myself a solution here, and the answer is 4.7. So that's good. Now that was using the side form. Let's do another example where we solve for an angle. So in this case I'm being asked to solve for the angle theta. Doesn't look like I've got an answer ready for this one. So in this case I'm looking for the angle theta, which is the same as the angle K. So, and I'm going to, as I've said, I really want to encourage you, if you're going to remember one form, a squared equals b squared plus c squared minus 2bc cosine of a. And now let's just go ahead and replace that for j, k, and l. So we're interested in the cosine of k, which means we're interested in the side k squared. And that means this is going to be j squared plus l squared minus 2jl cosine of capital K, but capital K is the same as theta. Now I bring this term over to the left side, so I get 2jl cosine theta is equal to j squared plus l squared minus k squared. Of course, if you have the formula given to you, then you just go ahead and use that. And now my last step, cosine theta is equal to j squared plus l squared minus k squared over 2jl. So the cosine of theta is equal to j squared. J is equal to 2, so that's going to be 2 squared, plus L squared. L is equal to 6, so that's going to be 6 squared, minus K squared, that's minus 5 squared, over 2 times J, which is 2, times L, which is 6. And that is equal to, again, you could do this all in one shot on your calculator if you wanted to. In this case, I'm going to take the time to, let's do this out a little bit more detail. So 2 squared is 4, 6 squared is 36, 5 squared is 25, so that's subtract 5 squared. 2 times 2 is 4, times 6 is 24. Cosine of theta is equal to 4 plus 36 is 40, minus 25 is 15 over 24. And this actually paid off. This is a nice clean fraction. And so if the cosine of this angle is equal to 15 over 24, then to get the angle by itself, I take the inverse cosine of 15 over 24. And I end up with theta is equal to the inverse cosine of 15 divided by 24 is equal to approximately 51.3 degrees. Now let's take a look. First of all, I'm going to double check a part of these calculations. Actually, you know what? I don't have any other reference. I don't have any other angles, so I don't know whether or not that's a reasonable answer. So all I can do from here is probably come back up to this point where I started putting numbers in, and I'm just going to check my calculations again. So this time I'm going to rely on my calculator rather than doing it all in my head. So 2 squared plus 6 squared minus 5 squared, and that's equal to 15. I got that part right. Divided by, and of course 2 times 2 times 6, I'm pretty comfortable with that idea. And then I take the inverse cosine of my answer, and once again I end up with 51.3. So I'm pretty confident that that's the correct answer for this one. Okay, so we're just doing those two examples, and so there's some assigned work. But now I'm going to go back and look at the derivation, give you an idea of where this is coming from. I might not even do the full derivation, but I at least want you to see it. So it's on the next 2 pages, and I'll show you those nice copies in a moment. But to start with, what we end up doing is just like we did with the sine law, which is I'm going to split this as into 2 right triangles. But the thing that's going to be different here is that as I work through these things, I'm also going to make use of the Pythagorean Theorem. Okay, so let's call this, once again, we've got our h value in between here. And so I need to incorporate this length c. And so I don't need, I'm going to call this a variable x, and I'm going to call this c minus x. So from here to here would be c minus x. From here to here it would be x. And we've actually done an example like this in class before where you have to do this kind of splitting things up. Okay, so Pythagorean Theorem. On this triangle on the left side, Pythagorean Theorem tells me that b squared is equal to h squared plus x squared. For the triangle on the right, Pythagorean theorem tells me that a squared is equal to h squared plus c minus x all squared. Okay, so then I go ahead and try to make a relationship with this. Well, let's expand this one out. A squared equals h squared plus, and this becomes c squared minus 2cx plus x squared. And then in this one, I've just got h squared plus x squared. Now this is where I'm going to get into some interesting ideas, because what I'm actually going to do is I'm going to notice that I've got an h squared and an x squared here. So another way I could write this is that a squared is equal to h squared plus x squared. I'm bringing those two together, and then I'll leave the rest of the stuff the same, plus c squared minus 2cx. And by doing this, I end up with h squared plus x squared is the same as this h squared plus x squared, which means I can replace h squared plus x squared with, I can replace h squared plus x squared with b squared. H squared plus x squared is equal to b squared. So a squared is equal to b squared plus c squared minus 2cx. And that's pretty good. If you think about the cosine law that we're trying to get, the cosine law is written a squared equals b squared plus c squared minus 2. Now what I want this to be, well, I don't like this x. This x doesn't actually do me any good. So what I end up doing is I have to find a way to replace x. So is there a relationship that I can come up with that will allow me to get rid of x? And to do that, we're actually going to come up here, and this time we're going to look at this left-hand triangle. I'm going to switch colors for this. Let's switch to green. So if I look at this triangle, what are some of the relationships that I can come up with? Well, I can relate using a right-angled triangle rule. I can relate A to x, b, and h. I want to relate it to x, so for the angle A, we have the opposite side. This is the hypotenuse, and this is the adjacent side. Now I definitely want to bring in the x, so I'm going to use the adjacent. If I use the opposite side, I'm reintroducing this variable h, which I actually got rid of before, because the h is this altitude that I made vertically. It doesn't really do us any good. So what I want to do is make use of the adjacent side, which is x, and the hypotenuse, which is b, and the angle a. And if you remember your SOHCAHTOA, S-O-H-C-A-H-T-O-A, that's your relationship among your trig ratios, adjacent and hypotenuse is cosine. So we can say that the cosine of the angle A is equal to adjacent over hypotenuse, which is x over b. And I'm trying to get rid of x, so I'm going to isolate x here. I'm just going to multiply through by b. So I end up with b cosine A is equal to x. And this x gets replaced with this x, which means instead of x, I write a squared equals b squared plus c squared minus 2. Well, I'll do it in two steps. 2c, and then instead of x, I'm going to write b cosine A. And just to clean that up a little bit, just to write it in a better order, a squared equals b squared plus c squared minus, I'm going to bring this b in front of the c, so I'll write that as 2bc cosine of a. And that is the cosine law for the side A, angle A relationship. I could do the exact same thing by putting in an altitude from the vertex A, from the vertex B, and go through these calculations, and I could come up with all three forms of the cosine law. So that's pretty interesting. The Pythagorean theorem and right-angle trigonometry allows us to come up with this fairly powerful formula to let us work on triangles that are not right triangles. We can still use a trigonometric relationship and a Pythagorean relationship, in fact. Okay, so that's it for this lesson. Let me just forward to the assigned work in case anybody's looking for that at the end of the video. And that is it for the cosine law.